A faint whisper drifts across the cosmos from the darkest places in space. These are the echoes from the abyss, the subtle signals we now capture from the most mysterious black holes. For centuries, they were only ghostly theories, but today they serve as real laboratories for the most extreme physics imaginable. By the end of this journey, you will see how these cosmic messages are fundamentally reshaping our understanding of reality. We will explore what happens to information that falls into a black hole and whether spacetime itself can be torn. How does the idea of a whisper from total darkness change your view of the universe? The universe itself is the instrument, a fabric of spacetime that can stretch and compress. Think of it as a silent pond, vast and perfectly still. When a monumental event occurs, like two black holes locked in a final, fatal dance, it is like a massive stone dropped into that pond. The impact sends ripples racing outward across the entire surface. These ripples are gravitational waves, the very echoes we now strain to hear. They are not made of sound or light, but are literal distortions in the fabric of reality, waves in spacetime itself. This was a cornerstone of Einstein's theory of general relativity, a prediction that waited a century for confirmation. That confirmation came in 2015, when the LIGO Observatory recorded the unmistakable chirp of two black holes colliding over 1 billion light-years away. In that moment, we did not just see the universe, we began to listen to it. Each wave is a cosmic message, encoded with the story of its violent birth. By reading the frequency and strength of these signals, scientists can rewind the clock. They can determine the masses of the black holes, how fast they were spinning, and the precise dynamics of their final, furious orbits. This ability to listen to spacetime itself delivers a profound lesson. The cosmos is not a static painting, but a dynamic, vibrant entity, constantly ringing with the echoes of invisible, energetic events. But to catch these faint whispers, we need devices of almost unimaginable sensitivity. The silence these instruments must isolate is almost deeper than the one in space. They are not telescopes pointed at the stars, but vast monuments to precision, built to feel the universe breathe. On the plains of Louisiana and the forests of Washington state, the LIGO observatories stand with arms stretching 4 kilometers long. Inside these vacuum-sealed tunnels, powerful lasers race down perpendicular paths, reflected by mirrors suspended with such delicate control that they are virtually free from every vibration of our world. The principle is one of profound simplicity and staggering sensitivity. When a gravitational wave passes through the Earth, it minutely stretches space in one direction and compresses it in the other. For that fleeting instant, one arm of the detector becomes infinitesimally longer than its twin. The laser beams, now out of sync by a distance smaller than a single proton, create an interference pattern that betrays the wave's passage. This is the whisper translated into data. To confirm these signals are not mere terrestrial rumbles, a global network listens together. The Virgo detector in Italy and the Kagr Observatory in Japan join the hunt, triangulating the cosmic source across the heavens. This international chorus of listening posts filters out the noise of our planet to find the true song of the cosmos, and our ears are growing even more attuned. The future LISA mission, a fleet of 3 spacecraft forming a gravitational wave observatory in the quiet of interplanetary space, will open a new, lower register of hearing. It will tune into the colossal mergers of supermassive black holes, events whose waves are too long and slow for any Earth-bound instrument to catch. This incredible sensitivity reveals a deeper truth. To hear the universe, we must first learn to be utterly, profoundly silent. Our greatest discoveries are emerging not from what we have built, but from the exquisite quiet we have managed to create. And the entities creating these cosmic ripples are the true titans of the abyss, black holes of such immense power that their collisions can momentarily outshine every star in the observable universe. These titans of gravity anchor the cosmos. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, a gravitational behemoth containing the mass of millions or even billions of suns. Its presence is so profoundly dominant that it governs the orbits of billions of stars, a silent conductor for an entire symphony of stellar motion. For decades, their existence was inferred, a shadow suggested by the frantic dance of stars at the galactic center. Then, in a stunning feat of global cooperation, the Event Horizon Telescope gave us our first direct glimpse. The now iconic image of the fiery ring and dark shadow of the black hole known as M87 star was not a photograph in the conventional sense, but a radio wave map of its violent immediate surroundings. It was our first real look into the abyss, confirming the monstrous scale of these entities. But these giants are far more than isolated destroyers. They are fundamental architects shaping their entire galactic ecosystems. Their immense gravitational pull acts as a cosmic regulator, influencing where and how new stars are born. In some cases, their ferocious energy output can heat surrounding gas, preventing it from cooling and collapsing into new stars. In others, the shock waves from their activity can compress gas clouds, triggering a firestorm of stellar birth. They are the ultimate example of creation through destruction. This dynamic is violently displayed in tidal disruption events when a star wanders too close. The black hole's gravity stretches the star, pulling it apart into a stream of incandescent gas. This material, heated to incredible temperatures as it spirals inward, creates a brilliant flare of light, a final, screaming echo of the star's demise. This reveals a profound lesson. Black holes are not the end of the story. They are central characters in the narrative of cosmic evolution, their gravitational might sculpting the very large-scale structure of the universe. To grasp their full impact, however, we must also listen to the whispers from their smaller, more volatile cousins. The drama of a stellar mass black hole begins with a star's final, defiant act. A star many times more massive than our Sun burns through its nuclear fuel in a cosmic blink, its inner furnace faltering. Without the outward push of energy, its own immense gravity wins a sudden and violent victory. The core collapses in less than a second, triggering a supernova explosion that can outshine an entire galaxy. What remains is not a star, but a stellar corpse, a black hole with the mass of a star crushed into a point of infinite density. This is the genesis of the most prolific gravitational wave sources we observe. These black holes are rarely alone. They are often born into binary systems, locked in a relentless gravitational dance with a companion star or even another black hole. Their orbital waltz is a slow, inevitable surrender. With every orbit, they radiate energy away in the form of gravitational waves, those faint ripples in spacetime. This loss of energy causes their orbits to tighten, drawing them ever closer in a cosmic spiral that can last for millennia. The final act is breathtakingly brief. In the last few milliseconds before collision, they whirl around each other at nearly the speed of light, churning the fabric of spacetime itself into a maelstrom. Then they merge. In that single, violent instant, the resulting collision unleashes more power than every star in the observable universe combined. It is a flash of pure gravity, a shout that echoes across the cosmos. We have now recorded dozens of these events, and each one is a gift. They provide a pristine laboratory for testing the laws of physics under conditions we could never recreate on Earth. In every case, the signal we detect perfectly matches the predictions of Einstein's theory of general relativity. Even in this most extreme environment, where gravity is at its absolute strongest, the theory holds. The echoes from these stellar corpses confirm that our understanding of spacetime is robust. Yet, these observations also raise a tantalizing question. What exactly happens in the space surrounding these objects during those final, frantic moments? This final, frenzied dance is a symphony written in spacetime itself. The two black holes, locked in their final orbits, whirl around each other in an ever-tightening spiral. This is the Inspiral, a phase that accelerates to a blur, reaching speeds approaching light itself. As they accelerate, the gravitational wave signal we detect transforms into a rising chirp, a clear, pure tone that rapidly sweeps upward in both pitch and volume. It is the universe's own countdown to a cataclysm. Then comes the main event, the merger. In a violent, asymmetric collision, the two distinct event horizons stretch, touch, and finally become one. This is not a gentle blending but a tumultuous reconfiguration of reality's fabric, an event so powerful it momentarily outshines the entire visible universe in raw gravitational power. The chirp ceases, replaced by a brief, explosive peak, but the story does not end there. The newborn black hole, misshapen and turbulent, must now find its peace. It begins to ring down, vibrating like a massive bell struck by a cosmic hammer. These vibrations are not sound, but oscillations of its very surface, shedding its deformations in a final, fading spectrum of gravitational waves. This three-part fingerprint, from the rising chirp to the explosive crash and the final hum, is a treasure trove of information. By analyzing the ringdown, scientists perform a kind of cosmic fingerprinting. The specific tones and decay rates of these vibrations are dictated solely by the black hole's final mass and spin. This exquisite match with prediction powerfully confirms the no-hair theorem, the elegant idea that a black hole is a fundamentally simple object described only by its mass, its spin, and its electric charge. All other details, all the complex information about what fell in, are seemingly lost forever, hidden behind the veil of the event horizon. They are the ultimate cosmic secret keepers. Yet, buried within the data, some faint, anomalous echoes suggest there might be more to the story, a subtle crack in this simple, powerful picture. But what if that final, fading hum is not the last word? What if our most powerful theories of gravity are subtly incomplete in the face of such ultimate darkness? Some of the boldest ideas in physics now suggest that the event horizon, that perfect one-way membrane, might not be so perfect after all. The extreme warping of spacetime right at the black hole's boundary could be governed by a new set of laws, a marriage of Einstein's gravity with the bizarre rules of the quantum world. This potential new physics might manifest as a physical structure, a quantum wall, or a region of intense fuzziness, lurking just outside the point of no return. Such a boundary would not let anything escape, but it would not let the gravitational waves leave so cleanly either. A fraction of the energy from the cataclysmic merger could bounce against this hidden surface. The main crash of the black hole collision would be followed, after a tiny delay, by a faint, repeating series of signals. These would be the true echoes from the abyss, not the main event, but its ghostly reverberation. Picture a lone shout in a vast, dark cavern. You hear the initial blast of sound, and then, a moment later, a softer copy of that sound returns, reflected from a wall you could not see. Scientists are now scouring the data from our gravitational wave observatories, searching for exactly this pattern buried in the noise after a black hole merger. They are hunting for the whisper that comes after the shout. The implications of a confirmed detection would be nothing short of revolutionary. It would be the first experimental evidence that Einstein's general relativity, our magnificent description of gravity, finally breaks down at the edge of a black hole. More profoundly, it would crack open a window into the theory of quantum gravity, the long-sought unification of the very large and the very small. This discovery would address one of the most perplexing paradoxes in all of science, the black hole information paradox. If these echoes are real, they could mean that information, the fundamental identity of everything that falls into a black hole, is not lost forever. Instead of being erased, that information might be slowly, subtly encoded into these faint gravitational reverberations, leaked back out into the universe over eons. The search for these echoes forces us to confront the most fundamental question of all: what truly happens at the final boundary, at the edge of forever? Is it a perfect, silent horizon, or is it a dynamic, structured surface, holding secrets about the deepest nature of reality itself? The answer may already be hidden in the data, a faint, repeating signature waiting to be heard. That dark shadow at the center of a fiery ring is the closest we can ever come to seeing a black hole directly. It is not the event horizon itself, for that boundary is fundamentally invisible, a perfect one-way street in the cosmos. The event horizon is a mathematical line in space-time, a point of no return from which the cosmic current becomes irresistible. Imagine standing at the very edge of a waterfall that plunges into an infinite abyss. You can stand right at the brink, but the moment your toe crosses that line, you are swept away for good. Nothing, not even a single particle of light, can swim back up that waterfall once it has fallen over the edge. This simple, brutal definition creates one of the most profound puzzles in all of science, the black hole information paradox. If you throw a book into a black hole, every piece of information that made that book what it is, from its words to its molecular structure, seems to be permanently erased from our universe when the black hole eventually evaporates. This violates a sacred principle of quantum mechanics, which states that information can never be truly lost. The event horizon is where this fundamental conflict between gravity and quantum theory plays out, a boundary where our known laws of physics are stretched until they snap. The brilliant ring of light we see in those landmark images is not the event horizon either. It is the photon sphere, a region just outside the point of no return where gravity is so intense that light itself is forced into a circular orbit. Photons, the particles of light, are trapped here, skimming the abyss like stones flung around a bottomless well. Some of this light manages to escape, creating that luminous halo framing the central darkness. The size and perfect circularity of that dark shadow are a direct test of Einstein's general relativity. If the shadow were lopsided, it would mean our understanding of gravity was flawed. So far, it has passed every test, confirming that spacetime behaves exactly as predicted even at this extreme frontier. Yet, the precise nature of the event horizon remains one of our greatest mysteries. Is it the perfectly smooth, featureless membrane that general relativity describes, or is it a chaotic, seething wall of quantum energy, as some newer theories suggest? To answer that, we must venture closer into the violent, swirling chaos that feeds the beast. This brilliant, swirling vortex of light is the black hole's dinner plate, a structure of unimaginable violence called an accretion disk. It forms from the cosmic debris that dares to venture too close, a relentless river of gas, dust, and even entire stars caught in the black hole's gravitational pull. This material does not fall straight in. Instead, it spirals inward like water circling a drain, gaining immense speed and temperature as it plummets toward the event horizon. The resulting disk glows with the heat of 1,000,000 suns, a radiant echo across the entire electromagnetic spectrum that broadcasts the black hole's secrets. The friction within this churning maelstrom is beyond comprehension. Particles of matter collide with unimaginable force, heating the disk to temperatures of millions of degrees. At such extremes, the material does not just glow with visible light, it screams in X-rays, emitting the highest energy radiation in the universe. By analyzing this brilliant, high-energy scream, astronomers can perform a kind of cosmic diagnosis. The specific properties of the X-ray light reveal the black hole's mass and, even more remarkably, how fast it is spinning. A rapidly rotating black hole drags the very fabric of spacetime around with it, twisting the inner edge of the accretion disk and imprinting a unique signature on the radiation we observe. But the feast does not always stay on the plate. Some of the infalling material, superheated and magnetized, gets channeled by incredibly powerful magnetic fields. These fields funnel the material away from the poles of the black hole, accelerating it into narrow, focused beams that blast outward at nearly the speed of light. These are relativistic jets, cosmic fire hoses that can stretch for hundreds of thousands of light years, far beyond their host galaxy. They punch into the intergalactic medium, injecting enormous energy into the cosmos and influencing the formation of new stars across vast distances. This transforms the black hole from a simple consumer into a powerful engine. Its feeding habits dictate the climate of its entire galactic neighborhood. A quiet black hole allows for a calm, structured galaxy. An active, feasting black hole with its brilliant disk and brilliant jets becomes a central power plant, its luminous echoes shaping the evolution of everything around it. The physics governing this chaotic dinner table are so extreme that they challenge our very understanding of matter itself. The silent, empty space around a spinning black hole is anything but still. Within a region called the ergosphere, the void itself becomes a relentless vortex. Picture a whirlpool so powerful that the very water is pulled into a spiral, and you cannot possibly stay in one place. This is frame dragging, a direct and dizzying consequence of Einstein's equations, where a rotating black hole pulls the fabric of spacetime around with it. Nothing within this distorted region can remain at rest, not even a perfectly stationary spacecraft with its engines off. Space itself is moving, and you are compelled to move with it, caught in a cosmic current born from pure spin. This incredible effect means that the black hole's rotation is not just a property, but a tangible source of energy. Theoretically, an advanced civilization could tap into this whirlpool of spacetime. By firing a projectile into the ergosphere to split it in two, with one piece falling in and the other escaping, you could extract rotational energy from the black hole itself. It would be like stealing energy from a cosmic carousel, slowing its spin to power a city, or perhaps an entire civilization. We measure this spin through the subtle fingerprints it leaves on the universe. The precise tone of a black hole's ringdown after a merger, detected in gravitational waves, reveals its final rotation. Meanwhile, the intense X-rays from its accretion disk carry a distinct signature, warped by the spacetime vortex just outside the event horizon. These observations confirm a stunning reality. Many black holes are born spinning rapidly, or they acquire a fierce rotation by feasting on surrounding matter over cosmic time. This spin is not a minor detail, it is a fundamental driver of the black hole's personality. A slowly spinning black hole is a placid well in space. A rapidly spinning one is an energetic dynamo, its frame-dragging effect stretching and twisting its surroundings, powerfully influencing how matter falls in and how its brilliant jets are launched. The hum of a quiet black hole and the roar of an active one are both dictated by the silent, relentless power of its spin. The personality of a supermassive black hole depends entirely on its dinner. At the heart of our own Milky Way, Sagittarius A star is a quiet giant, a gravitational titan slumbering in relative peace. It consumes only a trickle of interstellar gas, its brilliance a faint flicker compared to the billions of stars it governs. This is a dormant black hole, its immense power latent, its voice a low hum in the cosmic chorus. Now contrast this with a quasar. A quasar is that same fundamental object, a supermassive black hole in a state of ravenous, unimaginable feasting. When a rich supply of gas and dust floods its vicinity, the black hole awakens. Its accretion disk ignites into a maelstrom of light so intense that it can outshine every single star in its entire host galaxy combined. The difference is simply one of appetite. A quasar is gorging itself while a dormant giant is on a cosmic diet. This dramatic duality reveals a profound lesson. The same monstrous engine can appear as either a faint shadow or the brightest beacon in the cosmos, its identity shaped entirely by the fuel available in its immediate environment. We monitor these objects by watching their light flicker. These are not random blinks, but complex patterns of brightening and dimming that act as echoes, carrying detailed information about the structure of the accretion flow just milliseconds from the event horizon. By decoding this flickering stutter, we can map the chaotic dance of matter in the final moments before it vanishes forever. Understanding what triggers a black hole to switch from a quiet giant to a brilliant quasar is one of the great puzzles in modern astrophysics. It is the key to modeling how galaxies themselves are born, live, and die, for the activity of their central black holes directly regulates star formation across vast cosmic scales. And when a black hole sits down for its most dramatic feast, the resulting flare of energy is so colossal that its echo can be detected from the very edge of the observable universe, a shout from the abyss that travels for billions of years to reach our telescopes. A star's final journey is a spectacle of cosmic violence. On rare occasions, a sun-like star drifts into the gravitational sphere of a supermassive black hole. The side of the star closest to the abyss feels a gravitational pull immensely stronger than its far side. This difference, the tidal force, stretches the star horribly. It undergoes spaghettification, pulled into a long, thin strand of incandescent gas. This stream of stellar material wraps around the black hole, and a portion of it spirals inward, superheating to millions of degrees as it falls. The result is a brilliant flare of radiation, a final, screaming echo that can outshine its host galaxy for months. This is a tidal disruption event, the universe's most dramatic way of setting a place at the table. By carefully analyzing the light from this flare, scientists can perform a kind of cosmic autopsy. The way the light brightens and fades reveals the black hole's mass. The specific colors or spectrum of the emission tell a detailed story about the physics of accretion in this most extreme environment, a place where gravity is utterly dominant. These events are precious because they are so rare in any single galaxy, perhaps occurring only once every 10,000 years. But with modern automated sky surveys constantly scanning the heavens, we are now catching them with increasing frequency. Each new detection acts as a flare in the cosmic dark, revealing the presence of a supermassive black hole in a galaxy where it might have otherwise remained hidden and silent. This violent process confirms that black holes are not always quiet giants. They can announce their presence with a cataclysmic shout. Yet this destructive power is only one side of their nature, a prelude to their more subtle, creative role in the cosmos. These dueling titans are the workhorses of the new astronomy. The vast majority of the gravitational wave signals we have captured tell the story of two black holes locked in a fatal embrace. Each detection is a pristine laboratory, its clean, powerful signal carrying an unambiguous message about the masses and spins of the objects involved. This growing catalogue of collisions is revealing a cosmos far more dynamic and violent than we ever imagined. The way these pairs form is a tale of two paths. Some begin their lives as twin stars, massive siblings born together from the same cloud of gas. They live their stellar lives side by side, and if both are heavy enough, they each end their days in a supernova, leaving behind a binary black hole system. Other pairs are forged through chaos, meeting later in life within the crowded stellar dance of a globular cluster. A gravitational tango between three or more bodies can eject one star and leave two black holes bound together, a marriage arranged by pure chance. Population of these binaries is already rewriting the rules of stellar life and death. We are finding black holes with masses that theorists once thought were impossible, objects falling squarely into what was called the upper mass gap. Their existence challenges our understanding of the supernova explosions that create them, suggesting that some stars might collapse directly into black holes without a traditional, disruptive explosion, or that black holes can grow significantly through mergers in dense environments. Some of these wandering pairs are true cosmic renegades. An asymmetric supernova kick can send a newborn black hole flying out of its birthplace, and if it is already in a binary system, its companion gets dragged along for the ride. The result is a rogue black hole pair, ejected from its host galaxy entirely, destined to merge in the profound silence of intergalactic space. The simple, rhythmic chirp of their final Inspiral is a powerful echo from the void, confirming a key prediction of Einstein's theory while simultaneously challenging our models of how the universe builds its most massive objects. And the story may reach back to the very dawn of time, with some of these binaries potentially forming in the chaotic, dense environment of the early universe. Each new detection adds a data point, a single brushstroke that is slowly painting a revolutionary new picture of a cosmos teeming with invisible, circling giants. Black holes born from dying stars may not be the only kind. The universe's first darkness could have arrived in its infancy, mere instants after the Big Bang itself. In the primordial fireball, when all of existence was a seething, dense soup of energy, random fluctuations in density could have collapsed under their own gravity, not into stars but directly into black holes. These would be primordial black holes, relics forged in the universe's first moments. Unlike their stellar descendants, they were not born from the death of a star, and therefore they could theoretically be of any size, from a microscopic speck with the mass of a mountain to a colossal entity rivaling the giants at galactic centers. Their formation would have been a birth cry from the dawn of time. This ancient origin story makes them a compelling candidate for the universe's greatest mystery, dark matter. We know dark matter exists because its gravitational pull holds galaxies together, yet it emits no light and remains utterly invisible. What if a significant portion of this unseen mass is not some exotic particle, but a vast, hidden population of these primordial black holes, drifting like invisible icebergs through the cosmic sea? They would be the perfect dark matter candidate, massive and yet completely dark. Their mergers would tell a different story than the ones we currently detect. If two primordial black holes, each with the mass of a planet, were to spiral together, their collision would produce gravitational waves with a much higher frequency, a sharp, rapid chirp compared to the deeper thrum of stellar giants. Our current observatories are not sensitive to these frequencies, but future space-based detectors are being designed specifically to listen for this unique, high-pitched song of the ancient universe. Finding it would be like discovering a fossil from the first second of creation. The hunt for these echoes from the abyss is a profound scientific quest, connecting the largest scales of cosmology to the most extreme realms of black hole physics. It is a search for a hidden chapter in the cosmic story, a population of black holes with a genesis story entirely separate from stellar life and death. To confirm their existence would be to open a direct window into the conditions of the Big Bang, rewriting our understanding of the universe's first moments and finally illuminating the true nature of the dark matter that sculpts the cosmos. It would be the ultimate echo, a whisper from the very beginning of everything. This paradox strikes at the very heart of our understanding of reality. On one side stands quantum mechanics, with its fundamental law that information is never truly destroyed. If you burn a book, every single letter and word is, in principle, recoverable from the intricate pattern of smoke and ash. On the other side stands Einstein's general relativity, which dictates that anything crossing a black hole's event horizon is gone for good, its information erased from our universe forever. Both theories are spectacularly successful, yet they present us with an irreconcilable contradiction. Stephen Hawking identified a crack in this logical impasse. He realized that the void just outside a black hole is not entirely empty. Pairs of virtual particles, one with negative energy and one with positive, constantly flicker in and out of existence. Occasionally, right at the edge of the event horizon, this quantum fluke is torn apart. The negative energy particle falls in, reducing the black hole's mass, while its positive energy partner escapes into space. This slow leak is Hawking radiation, a faint whisper of heat that causes the black hole to gradually evaporate over astronomical spans of time. The problem is that this radiation is purely thermal, a formless hiss of random energy that seems to carry no details, no fingerprint, no story of what fell in. So when the black hole finally vanishes, where did all that information go? Was it truly erased, violating a sacred rule of the quantum world? This is the information paradox in its most vexing form. One radical proposal to solve it is the firewall hypothesis. It suggests that instead of a smooth, empty space at the event horizon, there is a literal wall of blazing high-energy particles. Anything striking this firewall would be instantly incinerated. This would preserve information by scrambling it at the boundary, but it creates another profound problem. It shatters Einstein's principle of equivalence, the very cornerstone of general relativity, which assures us that an astronaut falling into a black hole would feel nothing special as they crossed the horizon, no sudden wall of fire. We are left with a cosmic catch-22, where saving quantum mechanics seems to require breaking gravity. This is why the entire physics community is watching the hunt for gravitational wave echoes with such anticipation. If the event horizon is not a perfect, featureless boundary but has some kind of quantum structure, like a firewall or a fuzzball, it would reflect a tiny portion of the gravitational wave energy from a merger. Those faint, repeating signals would be the experimental signature we need. They would be the first direct evidence that our current picture of the event horizon is wrong, forcing a new theory that seamlessly blends gravity and quantum mechanics. The echoes from the abyss are not just ripples in space, they are potential messages from the edge of a new physics, carrying the answer to whether information truly lives forever. These subtle shudders in spacetime carry a message from the edge of known physics. The grandest quest in all of science is to find a single theory that unifies Einstein's gravity with the bizarre rules of quantum mechanics. For decades, this search has been a matter of pure thought, a mathematical puzzle without any experimental guide. But now we have a laboratory. The violent mergers of black holes are the only places in the universe where both gravity and quantum effects are simultaneously paramount, where the immense warping of spacetime meets the fuzzy uncertainty of the quantum world. The faintest anomalies in their gravitational wave signals could be the first experimental data for a theory of quantum gravity. Imagine the final ringdown of a newborn black hole, that fading hum as it settles into silence. According to classical general relativity, this signal should be perfectly smooth and clean. But if spacetime itself has a granular, discrete structure at the tiniest possible scale, as predicted by theories like loop quantum gravity, that final hum might be punctuated by a faint, repeating stammer. These would be the echoes not from a physical wall, but from the fundamental grain of reality. It would be like listening to a bell ring and hearing not a pure tone, but a subtle crackle within the sound, a signature of the metal's crystalline structure. Our most powerful theories suggest that spacetime might not be a smooth continuum, but a frothing, foamy sea of quantum fluctuations at the Planck scale. A dimension so infinitesimally small, it is to an atom what an atom is to our entire solar system. We could never hope to probe this foam in a terrestrial lab. The energy required is beyond colossal, but a merging black hole does this work for us. Its immense gravitational forces effectively magnify these microscopic features, imprinting their signature onto the gravitational waves that race out across the universe. By listening ever more carefully, we are using the cosmos as the ultimate particle accelerator. Each new black hole collision we record delivers a data point at energy scales we could never recreate. The precise shape of the gravitational wave signal, the exact nature of its ringdown, acts as a filter for our most ambitious theories. Does the data match the perfect black hole of general relativity? Or does it show the subtle deviations predicted by string theory or other candidates? We are no longer just astronomers, we are experimental physicists on a cosmic scale. The echoes from the abyss are not merely about understanding black holes. They are direct probes into the woven fabric of spacetime, carrying the answer to what reality is made of at its very foundation. These virtual laboratories are where the mathematics of the abyss comes to life. Since we cannot possibly recreate a black hole collision on Earth, we build them inside the world's most powerful supercomputers. This field is known as numerical relativity, a monumental effort to translate Einstein's immensely complex equations into a dynamic, visual simulation. The process begins by defining the starting conditions, the masses and spins of two black holes as they begin their final dance. The computer then divides the surrounding spacetime into a vast, three-dimensional grid and calculates how every single point on that grid warps and evolves over the microscopic steps of the collision. It is a computation of almost unimaginable scale, requiring months of processing time to simulate a merger that itself lasts less than a second. The final output is a breathtaking movie of twisting spacetime, and most importantly, a precise prediction of the gravitational wave signal the event would produce. This simulated echo is our Rosetta Stone. When LIGO or Virgo detects a real signal, the first thing scientists do is compare its squiggle to a massive bank of these pre-calculated templates. It is like having a cosmic fingerprint database. By finding the simulated waveform that best matches the observed data, we can instantly read off the properties of the source, determining the black hole's masses and spins with astonishing accuracy. This synergy between digital prediction and real-world observation revealed a phenomenon that was purely theoretical until recently: the black hole kick. When two black holes merge asymmetrically, if their spins are misaligned or their masses are very different, the gravitational waves carrying away energy and momentum can be shot out more strongly in one direction. To conserve momentum, the newborn black hole recoils in the opposite direction, like a cannon firing. The simulations showed these kicks could be powerful enough to reach thousands of kilometers per second, easily exceeding the escape velocity of even the largest galaxies. A black hole born from such a violent merger could be sent flying, ejected from its galactic home entirely to wander the dark intergalactic void. This incredible prediction, born entirely from supercomputer models, gives us a new way to interpret the silent, empty spaces between galaxies, wondering if they are patrolled by these invisible rogue giants. Our ability to listen to the cosmos is therefore guided by our ability to simulate it first. The computers tell us what to listen for, and the universe, in its violent beauty, answers. The hunt for cosmic truth is no longer a solitary pursuit. This new era is defined by a coordinated effort, a global network of instruments listening and watching in unison. We call this multi-messenger astronomy, a symphony of observation where each instrument plays a different part. The most powerful discoveries now come from combining different cosmic messengers, from the silent ripples of gravitational waves to the brilliant flash of light, and even the ghostly passage of neutrinos. Each one tells a different part of the same story. A landmark event in 2017, known as GW170817, proved the incredible power of this approach. It was the collision of two neutron stars, detected first as a long, rumbling chirp in gravitational wave observatories. Within moments, an automated alert shot across the globe, triggering a frantic, coordinated race. Telescopes of every kind on Earth and in space swiveled to pinpoint the source. They caught it, a brand new kind of cosmic explosion, a kilonova, glowing with the light of forged gold and platinum. For the first time, we witnessed the same cataclysm through two completely different senses, hearing the spacetime crash and seeing the brilliant aftermath. This single event confirmed that the heaviest elements in the universe, like the gold in a wedding ring, are forged in these incredible stellar collisions. For black hole mergers, a coincident light show is far more rare. Their pure gravity collisions typically occur in the void, leaving only a whisper in spacetime. But if two black holes merge within a dense cloud of gas, their immense gravity can violently stir that material, heating it enough to produce a fleeting but detectable flash across the electromagnetic spectrum. Catching that flash requires an unprecedented level of international coordination. The gravitational wave signal provides a rough sky map, a vast area of possibility. Then, within minutes, observatories from every continent must scan that enormous region, searching for a new pinprick of light that was not there before. It is a cosmic needle in a haystack, a testament to human collaboration. When it works, the result is transformative. The gravitational waves reveal the masses and spins of the black holes, the fundamental dynamics of the merger itself. A coincident electromagnetic signal, should one appear, would tell us about their environment, the density of the gas around them, and the immediate aftermath of their violent union. This combined dataset is infinitely richer than any single observation. We are no longer just listening to the universe or just watching it. We are experiencing it with multiple senses, building a complete, three-dimensional understanding of its most violent events. This collaborative watch, this new paradigm of exploration, is where the next great echo from the abyss will be found, not by a single telescope, but by a chorus of them all singing in unison. This invisible connection weaves through the cosmos, tying one great mystery directly to another. The nature of dark matter, that elusive substance whose gravity binds galaxies together, remains one of science's most profound puzzles. For decades, the leading candidate has been a hypothetical, exotic particle. Yet another possibility lingers in the shadows, the idea that some or even all of this dark matter could be made of black holes. Not the stellar mass giants born from dying stars, but the primordial kind, ancient relics forged in the universe's first chaotic moments. These would be the ultimate dark matter, massive objects that emit no light whatsoever, drifting through the galactic halo like a vast, invisible archipelago. The challenge is that our observations have placed these primordial black holes under tight scrutiny. If they were too common or fell within certain mass ranges, their collective gravity would subtly distort the light from distant stars, an effect we have not seen in sufficient numbers. Current data tells us that while they could exist, they cannot make up 100% of the dark matter. They might be a component, a fraction of the cosmic inventory, but they are unlikely to be the sole answer. This realization shifts the question. Instead of asking if black holes are dark matter, we now ask how dark matter and black holes interact. Every galaxy is embedded within a vast, diffuse sphere of dark matter, a halo that extends far beyond its visible stars. This halo's gravitational pull is the dominant architectural force shaping the galaxy's very structure. It acts as a cosmic guide, influencing the paths of everything within it, including black holes. In dense, crowded environments, dark matter's gravity can funnel stellar mass black holes toward the galactic center over billions of years. This process promotes encounters, pairs them up, and increases the chances of them eventually spiraling together in a violent merger. The invisible hand of dark matter is subtly choreographing the dance of the abyss. This means the gravitational wave signals we detect are more than just messages from colliding black holes. They are indirect probes into the dark matter environments where these black holes were born and lived. By building a large catalog of mergers and analyzing their statistics, their rates, and their mass distributions, we can perform a kind of cosmic archaeology. A higher than expected rate of massive black hole mergers in certain galactic environments could be a telltale signature of a particularly dense or uniquely structured dark matter halo. The echoes from the abyss carry an imprint of the invisible sea they swam through. This creates a beautiful, symbiotic relationship between two of the universe's greatest secrets. Dark matter shapes the evolution and merger history of black holes, and in turn, the population of black holes we observe through gravitational waves sheds light on the properties of the dark matter itself. Unraveling one mystery provides the essential clues to solve the other, a powerful reminder that in the cosmos, nothing exists in true isolation. Each new chirp from the abyss adds another face to the cosmic census. We are no longer just witnessing random cataclysms. We are compiling a vast statistical survey of the universe's hidden black hole population. The collective properties of these detections, their masses, spins, and distances, are painting a revolutionary picture of demographic trends on a galactic scale. The data is speaking, and it is telling us that our previous ideas about stellar death were incomplete. We have discovered that binary black holes with a total mass between 50 and 150 times that of our Sun are surprisingly common. This was a genuine shock. According to established models of stellar evolution, the violent supernova explosions that create black holes should tear apart stars in this mass range, leaving nothing behind. Their frequent appearance in our gravitational wave data forces a radical rethink. Perhaps some of the most massive stars do not die in a traditional supernova at all. Instead, they may undergo a direct collapse, their immense core quietly vanishing into a black hole without a brilliant, disruptive farewell. This silent death would leave behind the heavy black hole binaries we are now routinely detecting. The story deepens when we examine their spins. The measurements of black hole rotation show a fascinating variety of orientations. Some pairs spin in perfect alignment, like a perfectly synchronized dance duo, suggesting they were born together from a binary star system and lived their entire lives in a stable, coupled existence. Others, however, have wildly misaligned spins, a clear sign of a more chaotic origin. These pairs likely found each other later in life within the dense, stellar environments of globular clusters, where gravitational encounters can randomly toss black holes into a binary partnership. This single demographic detail, the spin orientation, acts as a forensic tool, allowing us to trace the life history of these dark objects. As our catalog of detections swells into the hundreds, this big data approach will answer the most fundamental questions of stellar life. How do the most massive stars truly end their lives? What are the dominant cosmic environments where black holes find their partners? We are transitioning from the study of individual monsters to understanding the life cycle of an entire invisible population. This is the new revolution. Black holes have ceased to be isolated curiosities and have become a statistical sample, a powerful new lens through which we can read the grand story of stellar and galactic evolution. Our current listening posts are like the first crude radio receivers, catching only the loudest shouts from the cosmos. The next generation of observatories will hear the whispers. Projects like the Einstein Telescope, to be built deep underground, and Cosmic Explorer, with arms 10 times longer than LIGO's, will be so sensitive they could detect a black hole merger at the very edge of the observable universe. Their advanced isolation from seismic noise and improved laser power will open a vast new volume of space to our ears. We will not just catch the final, frantic seconds of a collision. We will be able to tune into the opening movements, listening for hours or even days as supermassive black hole binaries spiral inward in a slow cosmic dance. This will transform these events from brief crashes into entire symphonies, where every note of the Inspiral reveals the history and environment of these colossal binaries. Alongside them, the space-based LISA mission will float in formation, a triangular observatory with sides millions of kilometers long. Free from the rumble of Earth, it will listen to a lower register of gravity's spectrum, the domain where million solar mass black holes sing. It is the difference between hearing a single violin and suddenly being able to hear the entire string section of the cosmic orchestra. The data deluge will be immense. The sky will not be silent between major events. Instead, it will thrum with a permanent gravitational wave background, a static hiss composed of the overlapping chirps from every black hole merger in the universe, too faint and numerous to be distinguished individually. This cosmic hum will be a new tool for precision cosmology, allowing us to measure the expansion rate of the universe and stress test Einstein's relativity in ways we can only dream of today. The future is not about hearing louder crashes, but about discerning an infinitely richer and more complex chorus. To understand this chorus, however, our theoretical models must evolve just as rapidly as our machines. But the black hole may not be the only monster lurking in the gravitational wave data. The signals we interpret as colliding black holes fit Einstein's predictions with stunning accuracy, yet some theorists are asking a dangerous question. What if we are misinterpreting the echoes? What if some of these dark objects are not black holes at all, but something even more bizarre? Imagine a tunnel through the fabric of spacetime itself, a wormhole. While firmly in the realm of theory, a stable, traversable wormhole would require matter with truly exotic properties, possessing negative energy. If two such structures were to spiral together and merge, the resulting gravitational wave signal would initially look almost identical to a black hole collision. The crucial difference would come at the very end. Instead of the clean ringdown of a new event horizon, the merged wormhole might not settle immediately. It could oscillate, its throat vibrating, producing a series of faint, repeating gravitational wave echoes long after the main crash has faded. These would be the true signature of a tunnel in space-time, a ghostly reverberation that a black hole simply cannot produce. Another hypothetical creature is the gravistar, a star made not of matter but of a core of dark energy enclosed by a thin, super-solid crust. It would look like a black hole from the outside, but it would possess no event horizon, no point of no return. A collision between two gravastars would also create a distinctive echo, as their exotic interiors slosh and vibrate in ways a simple black hole cannot. The hunt for these subtle deviations is not a fringe pursuit. It is a fundamental drive to test the limits of our knowledge. We are actively searching the data from every observed merger, scouring the quiet that follows the storm for any sign of a repeating whisper. Finding such an echo would be a discovery of epic proportions. It would mean that some of the dark hearts we have been cataloging are not black holes, but members of an entirely new family of celestial objects, things we currently only write equations about. This theoretical exploration ensures we keep our minds open to the universe's full potential for strangeness. The echoes from the abyss might be hiding a surprise that rewrites every textbook on gravity. Our journey into the unknown demands not just better detectors, but the courage to imagine the truly unimaginable. Our very existence might depend on the silent presence of these cosmic giants. This is the heart of the anthropic principle, a profound idea suggesting that the universe we observe must be compatible with the conscious life that observes it. And black holes appear to be a fundamental part of that compatible universe. Consider the supermassive black hole at the center of our own Milky Way. Its immense gravitational pull acts as a hidden anchor, helping to bind our galaxy's vast spiral structure together. Without this central, stabilizing mass, galaxies could be far more chaotic and unstable, their stars scattered into the void. But the role of these giants goes far beyond mere gravity. Their energetic output, especially during their brilliant quasar phases, acts as a cosmic regulator. When a supermassive black hole feeds, the resulting winds and radiation heat the surrounding galactic gas. This prevents the gas from cooling too quickly and collapsing into a firestorm of new stars. Without this feedback, a galaxy would burn through its stellar fuel in a brief, furious burst, leaving behind a dead galaxy, devoid of the long, stable periods necessary for life to emerge and evolve on planets like our own. The connection runs even deeper. The stellar mass black holes we detect through their collisions are born from the deaths of the most massive stars. Those same supernova explosions are the universe's primary forges for heavy elements. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all blasted into space by the cataclysmic deaths of stars that ultimately left behind black holes. A universe without black holes would likely be a universe without these essential building blocks for planets, oceans, and life itself. This leads to a staggering realization. Our ability to sit here and ponder the nature of black holes may only be possible because black holes exist. They help create the stable, long-lived, and chemically rich cosmic environment that allows observers to arise. The darkness of the abyss and the light of consciousness are not separate stories, but intertwined threads in the same cosmic fabric. That first image of a black hole's shadow did not just travel through space, it traveled across every screen on Earth. In an instant, a complex mathematical certainty became a shared cultural icon, a symbol of humanity's reach into the cosmic dark. Why does a singularity of infinite density, a place where physics breaks down, resonate so deeply with people who will never see the equations that describe it? It is because black holes are the final frontier in a very literal sense. They are the ultimate boundary, the point beyond which our knowledge simply stops. This touches something primal within us, the same drive that made ancient cultures map the stars and chart the unknown seas. It is the human desire to look into the abyss and not only wonder what is there, but to find a way to see it. The scientists who brought us that image understood this. They did not just publish a paper, they held a global press conference, translating years of painstaking work into a simple, powerful statement. We saw it, we saw the unseeable. This translation is an art form in itself. Complex data becomes a vibrant visualization. The sterile squiggle of a gravitational wave becomes an audible chirp that anyone can hear and feel. These are not simplifications, they are bridges, built by astronomers and science communicators to connect the frontier of research with the public's innate curiosity. That connection is the lifeblood of science. A child who sees that fiery ring might be inspired to become the physicist who solves the information paradox. A taxpayer who understands the grandeur of listening to spacetime might continue to support the basic research that makes it possible. This cycle of wonder and discovery is what propels us forward. The story of the abyss is at its heart a human story. It is a narrative about building impossibly sensitive machines, about international teams working in concert, and about the stubborn refusal to accept that any part of the universe is beyond our capacity to learn about. Every new echo we detect adds another verse to this story, a story we are all writing together. Our detectors are not listening in a silent universe. The raw data stream is a cacophony of terrestrial noise, a constant roar that masks the subtle whispers we seek. Every minute vibration of the Earth becomes a competing voice. The distant crash of ocean waves on a continental shelf, the rumble of a freight train miles away, even the collective hum of human activity. All of this creates a seismic background that constantly jostles the exquisitely sensitive mirrors. Finding the faint chirp of a black hole merger billions of light years away is the ultimate exercise in cosmic eavesdropping. It is the challenge of identifying a single, specific whisper in a stadium filled with a screaming crowd. To solve this, scientists turn to a powerful technique called matched filtering. Imagine you have a library containing the precise sound of every possible black hole collision, each unique waveform predicted by supercomputer simulations. The algorithm takes this library and rapidly compares it to the noisy data stream, sliding each theoretical template across the mess of interference. When it finds a near-perfect match, a signal emerges from the chaos with stunning clarity. This is how we transform an indecipherable rumble into a clean, readable chirp that tells a story of mass and spin. But what if the universe contains collisions we have not yet imagined? This is where machine learning enters the hunt. These artificial intelligence systems are not given a specific library of sounds to match. Instead, they are trained on both real and simulated data, learning the subtle characteristics of a genuine gravitational wave. They then scan the endless noise, searching for any anomaly that bears the hallmarks of a cosmic event, even if its pattern does not resemble anything in our current catalog. This opens the door to discovering entirely new classes of sources, objects or collisions that defy our current theoretical expectations. The sheer scale of this data challenge is monumental. A single observing run can generate petabytes of information, requiring immense computational power and innovative statistical methods to process. This endeavor is a profound collaboration, uniting not only astrophysicists but also data scientists, computer engineers, and statisticians. Behind every clean, elegant chirp that announces a discovery lies a mountain of human ingenuity and relentless technological refinement. The clarity of the cosmic message is entirely dependent on the quality of our silence and the sophistication of our tools to hear within it. This grand endeavor, listening to the whispers of spacetime, does not come without a significant price. We pour immense resources into building colossal machines that probe phenomena with no obvious, immediate benefit to our daily lives. It is a fair and vital question to ask why. Why should we invest so deeply in understanding the final moments of a black hole collision billions of years away? The answer lies not in a single justification, but in the layered value of pure, fundamental research. History provides the most compelling argument. Time and again, our quest to comprehend the universe's basic rules has yielded technologies that reshape human civilization. The development of Einstein's theory of general relativity is a perfect example. For decades, it was a beautiful but seemingly abstract description of gravity. Today, its equations are absolutely essential. Without accounting for the subtle warping of spacetime around Earth, the satellites in our global positioning system would fail. Their navigation signals would drift by miles each day, rendering the technology we rely on for travel, commerce, and communication utterly useless. The pursuit of gravitational waves has driven the perfection of laser interferometry to an almost unbelievable degree. The need to measure a change in distance smaller than a proton has pushed the boundaries of precision engineering. This technology now finds applications in fields far from astrophysics, from detecting microscopic defects in advanced materials to developing new, highly sensitive medical imaging devices. These are not the goals of the research, but they are its powerful and unpredictable dividends. We are planting seeds for a technological forest we cannot yet see. Yet the value transcends practical spin-offs. This research speaks to something profoundly human, an innate drive to explore and to understand our context in the vast cosmos. Knowing that we can decode the final dance of two invisible giants in a distant galaxy changes our perspective on our own existence. It enriches our culture, adding a new chapter to the epic story of human curiosity. It becomes part of our shared intellectual heritage, a monument to our species' capacity to ask profound questions and build the tools to answer them. Investing in this long-term, curiosity-driven science is ultimately a statement about the civilization we wish to be. It declares that we value knowledge for its own sake, that we believe understanding the universe is a worthy endeavor in itself, regardless of its utility. This ethical framework, this commitment to exploration for the sake of wisdom and wonder, is what truly justifies our journey into the unknown, ensuring that the echoes we chase illuminate not just the cosmos, but our own place within it. The most profound lesson from the abyss might be the one it refuses to teach. Deep within the black hole's heart lies the singularity, a point where the known laws of physics cease to function. Here, matter is crushed to infinite density, and the elegant equations of Einstein break down into meaningless infinities. This is the ultimate barrier, a place that may be permanently veiled by the event horizon. The principle of cosmic censorship proposes that nature itself enforces this privacy, that the deepest chaos of the universe is always hidden from our view. It is a cosmic fail-safe, preventing the unpredictable physics of the singularity from affecting the orderly universe outside. We can listen to the echoes from the very brink, but the true core of the mystery may remain forever locked away, a secret the cosmos keeps for itself. This hidden boundary defines the very edges of scientific inquiry. It forces us to ask a humbling question. Could some truth simply be beyond the grasp of a human mind that evolved to navigate a world of moderate speeds and gentle gravity? Our tools and our intellect are products of this universe, and they may have inherent limits when confronting its most extreme conditions. The quest then shifts. Instead of seeking final answers, we learn to map the shoreline of the unknowable. Each gravitational wave we detect, each flicker of light from an accretion disk, is a message from that shoreline. It tells us not what lies in the absolute darkness, but how far our light can reach. This is not a failure of science, but a recognition of its true context. The universe is under no obligation to be fully comprehensible to us. Its enduring mysteries, like the silent heart of a black hole, are what fuel our endless curiosity and give the echoes from the abyss their timeless, haunting power. The equations that describe a spinning black hole possess a stunning, almost musical symmetry. This is the Kerr solution, a set of formulas so elegant and powerful they can predict the entire gravitational landscape around a rotating abyss using only two numbers, its mass and its spin. There is a profound beauty in this simplicity, a sense that the universe, in its most extreme states, operates on principles of breathtaking grace. This aesthetic is not just a happy accident, it is a guiding light for theorists. Time and again throughout the history of physics, the mathematically beautiful idea, the one with the most symmetry and elegance, has proven to be correct. The hunt for a theory of quantum gravity is in many ways a search for the most beautiful mathematics that can stitch the cosmos together. When we witness the intricate chaos of a black hole merger in a supercomputer simulation, we are not just watching a data visualization. We are seeing a ballet written in the language of spacetime, a violent yet perfectly ordered transformation governed by these same elegant rules. The brilliant, fiery ring that captivated the world in that first black hole image is a direct manifestation of this beauty. It is a cosmic hall of mirrors, a photon sphere where light is trapped in a circular orbit, creating a perfect halo of warped starlight around the central darkness. The interplay of light and gravity here creates scenes of unparalleled grandeur, where entire galaxies are lensed into shimmering arcs and the fabric of reality is painted with the brushstrokes of pure geometry. To appreciate this is to engage both halves of the mind. The analytical left brain dissects the equations, while the creative right brain marvels at the sublime image they produce. This fusion makes the study of black holes more than a scientific discipline. It becomes a deeply human pursuit, driven by the same sense of wonder that an artist feels before a masterpiece. The abyss does not only whisper secrets, it sings them with a terrifying and beautiful voice. The tools we build to listen to the abyss rarely remain confined to astronomy. The relentless pursuit of measuring a whisper in spacetime has forged new technologies with a life of their own. Consider the laser interferometry at the heart of gravitational wave detectors, a system of such impossible precision it can sense a shift smaller than a single proton. This is not just a tool for cosmology, it is a new benchmark for measurement itself. These same principles are now being adapted to create more stable platforms for inertial navigation, which could one day guide aircraft or submarines with unprecedented accuracy without any need for external signals like GPS. The quest to hear the cosmos is quietly revolutionizing how we measure motion on our own planet. The challenge of finding a single cosmic chirp in a sea of terrestrial noise has spawned equally powerful innovations in data analysis. The sophisticated algorithms developed to filter out that noise and identify the subtle signature of a black hole merger are now being applied to entirely different domains. In the world of finance, similar pattern recognition techniques are used to detect subtle, fraudulent signals within the vast, chaotic torrent of global market data. In medicine, these advanced statistical methods are helping to enhance medical imaging, teasing out clearer signals from MRI scans to identify tumors or neurological conditions at earlier, more treatable stages. A mathematical strategy born from listening to colliding black holes can, quite literally, help save lives. Even the supercomputers running these monumental simulations are being pushed to their absolute limits. The field of numerical relativity, which models the violent dance of black holes, demands a scale of computation that was once unimaginable. To simulate a single second of a merger, these machines must solve Einstein's fiendishly complex equations across a three-dimensional grid representing all of spacetime around the event. This forces constant innovation in computer science, driving the development of new algorithms for parallel processing and data management that then trickle down to benefit climate modeling, pharmaceutical design, and materials science. The digital black holes we create are laboratories for the future of computing itself. Perhaps the most surprising ripple effect touches the realm of philosophy. The profound puzzles posed by black holes, like the information paradox, have reinvigorated centuries-old debates about the nature of reality and the limits of human knowledge. They force philosophers of science to grapple with difficult questions. Is a black hole's singularity a real physical object, or just a sign that our current theories are incomplete? When two different theories can explain the same observational data, how do we choose between them? The strange, counterintuitive nature of the abyss challenges our most basic assumptions about explanation and truth. This demonstrates that the value of probing the cosmos extends far beyond practical gadgets. It nourishes the very way we think about knowledge and existence. The echoes from the abyss do not just cross space, they resonate across the entire landscape of human inquiry, reminding us that a discovery in the darkest corners of the universe can illuminate countless other fields. This grand adventure is driven by a quiet, persistent curiosity that lives within each of us. When a scientist spends years refining a single algorithm to filter noise from a gravitational wave signal, or an engineer works to stabilize a mirror against the faintest tremor, they are answering a call that is fundamentally human. It is the same call that has guided explorers across oceans and into the deepest caves, a deep-seated need to see what lies just beyond the known horizon. Their work is a testament to patience, a quality often lost in our fast-paced world. A single discovery might be the culmination of decades of collective effort, a breakthrough built upon the stubborn dedication of thousands of people across the globe. For you, the viewer, learning about these discoveries is an invitation to join that collaborative effort. Every time you grasp the scale of a supermassive black hole or feel the awe of a spacetime ripple, you are expanding your own mental model of the cosmos. You are not just receiving information, you are participating in the age-old human story of exploration. This journey challenges you to think in scales that defy everyday intuition. Contemplate a collision that occurred when life on Earth was just single-celled organisms, its echo only now reaching us. Consider the sheer emptiness of intergalactic space, where rogue black holes drift in perfect silence. Wrestling with these concepts stretches the mind, offering a profound sense of perspective on our own place in the grand scheme. This personal connection to the cosmos is perhaps the greatest gift science offers. It reminds us that we are not merely observers, but active participants in a vast, dynamic, and mysterious universe. Our curiosity is the engine of this participation, a powerful force that propels us to build better detectors, to write more elegant equations, and to simply listen more carefully. The echoes from the abyss are far more than data points on a graph. They are a conversation with the cosmos, a dialogue written in the language of gravity, and we are only just beginning to learn how to listen. The abyss has spoken, and its echoes have taught us that darkness is not silent. Our journey has transformed black holes from cosmic ghosts into vibrant sources of information, each gravitational wave a verse in the story of spacetime itself. We learned to listen to the universe breathe, to feel the ripples from collisions that momentarily outshine all the stars. We saw the unseeable, framing the shadow of an event horizon with a fiery ring of light. These discoveries reveal black holes as fundamental architects, their immense gravity sculpting galaxies and regulating the birth of new stars. They are the ultimate cosmic laboratories, testing the laws of physics under conditions we can never recreate. The key lesson is their dynamic nature, from the quiet slumber of a dormant giant to the brilliant flare of a quasar in its feasting phase. They are not endpoints, but active participants in the evolution of everything we see. As our instruments grow ever more sensitive, the coming whispers will probe the very fabric of reality, perhaps revealing the quantum structure of spacetime or even more exotic objects hidden in the data. Let this exploration leave you with a renewed sense of wonder when you gaze at the night sky, knowing that in the quiet dark, a profound and beautiful cosmic conversation is ongoing. If this journey into the universe's greatest mysteries captivated you, consider subscribing for more deep dives. We would love to hear which echo from the abyss resonated most with you, so feel free to share your thoughts in the comments below.